Yeah, you can start. And thank all the committee for spending time with us all over the world. And I really appreciate that.
Yeah. Okay, thank you, Dr. Han. So, hi everyone, this is Yuhan. So, I'm currently a PhD candidate from Dr. Zhu Han's research group at the ECE department at the University of Houston. So, thank you very much for your time to attend my dissertation defense presentation. So, the title of my dissertation is Synergies of Meaningful Games in Machine Learning and 6G Communication Networks. So here's outline of my today's presentation. So I will first give a brief introduction of what a meaningful game is, and then I will introduce some of my works using meaningful games for applications in machine learning and 6G communication networks. Okay, and later on, I will conclude my presentation and show my future works. Um, what is meaningful game? Typically speaking, meaningful game is a model to study the group behavior for large population system by utilizing the group state distribution. And by modeling the group behavior, the system model will be simplified significantly. And actually, there are many natural large population systems in our world. For example, in these two figures, there's a reef fish swimming like a hurricane and ship running in fear of a drone. And here's a two example to illustrate what meaningful game is. It is fish catching game. So in this figure, there's a fishing man and a fish swarm. I'm sorry. So the goal of the fisherman is to catch the fish, while the goal of the fish is to being caught by the man. While to find optimal swimming strategy for the both fish and man. So in traditional solution, every fish needs to react to every other fish and the fishing man, while the man needs to react to every single fish. While since there is a large number of fish in this scenario, and it will be very complex in a traditional solution. Well, in a meaningful game solution, the fish strategy are approximated by a so-called mean field term, which is basically the group state or action distribution. So in this way, every fish only needs to react to the fish group and the man only needs to react to the fish group. So in this way, the system model will be simplified significantly. So actually, meaningful games have many promising applications. For example, this UAV's control, this robot path planning, or the power control in some ultra-dense device-to-device networks, or for some machine learning, such as the data augmentation, which is also one of my works, and edge computing and some academic models. So here's graph to illustrate what's the relationship between the optimization theory and game theory. So basically, in the optimization problem, there's only one agent, and this agent only needs to optimize his own cost function, which is just a function of itself control variable. Well, in the game theory, there are many agents, not just one, and the difference is that one agent's cost function is not just a function of itself control, but also a function of other agents control here. While in the optimal control problem, there's also one agent. While different from the optimization problem, there's an extra constraint function that describes how this agent state is influenced by its control. Well, in a differential game, there are many agents, and there's also one extra constraint thing that the one agent's state it's not just a control influenced by its control, but also influenced by other control. Well, in a meaningful game, here every agent state or the control are summarized into so-called mean field term rho here, and the agent's states is influenced by its own control and the whole state mean field here. So here's a typically a mathematical format of a very classical mean field game. There's here the cost function includes two parts. One is the agent's running cost, which happens during all the time slot from 0 to upper letter t. And there's another cost function, which is the terminal cost that happens only at a terminal time, which is a function of agent's terminal state and the whole population's terminal state. and we are trying to maximize the agent strategy alpha here to minimize the whole cost function. And for the constraint function, the first one is a so-called Fokker-Planck equation. It would just show how the whole population's state dynamics evolves with time. And the second constraint is just the boundary condition that describe the initial state distribution of these populations. And so to solve this problem, there are many methods. So one very classical one is just to iteratively update the so-called Hamilton-Jacobian-Bellman equation and the Fokker-Planck equation iteratively to get optimal solution. So here, this AJB and FBK equation here is just the KKT condition of this optimization problem. So we just iteratively update them until convergence to get the solution of this Milford game problem. Yeah. So later I will introduce some more numerical methods to solve the Milford game problem. Okay, so then I would like to introduce my first work that utilizing mean-field games, which is using mean-field games for the vehicular edge computing. So first of all, what is vehicular edge computing? Well, vehicular edge computing is a paradigm that an edge server performs data processing tasks for nearby vehicles. And such paradigm can help to release the high computation load of vehicles and speed up the task response times and enhance data processing. So such vehicular edge tasks usually includes some like the intersection safety warning, the emergency electronic brake, and the high definition map. So actually there are many characteristics of such VEC applications. For example, since the vehicles are moving at a very high speed, and there are pedestrians and red lights, green lights, and so on, traffic lights. So the environment information is always dynamic and need to be uploaded timely. And also some vehicular tasks are very time sensitive. For example, this emergency electronic brake. So such tasks should be finished in a very short time latency. And also some tasks are very huge. For example, the data size of the 3D chip is very huge. So considering such characteristics and challenges, here we focus on to design a fast offloading mechanism for this vehicular edge computing. And here we'll propose to use mean-field game. So why is that? This is because improving the data offloading performance, such as the latency requirement and energy efficiency for those time-sensitive vehicular applications, is a key challenge faced by the current vehicular edge computing. Well, the computation time, or say the training time of some learning-based method of existing offloading mechanism is very long and cannot meet the vehicle's latency requirement, especially when the number of vehicles is large. And so here we have mean-field game. Mean-field game is able to reduce the computational complexity and therefore reduce the latency. So here is the system model of my considered scenario. So we have many vehicles here, and we have each access point and each server. So these vehicles are equipped with sensors such as GPS, the LiDAR, the radar, the camera, and so on. I'm sorry. And each access point connects with each servers through the optical fiber here. And here's in the right figure here, here's the workflow of the edge task. So at the first step, the sensors at the vehicle side will generate some data. So this sensor includes the GPS, camera, LiDAR. And after the data generation, the data will be then sent to the middleware in the vehicle side for some data pre-processing and data organization. And after that, the pre-processed data will be sent from the vehicle side to the edge server side through some communication unit. So this is called offloading. And then the offloaded data will be processed by the edge server, and finally the tasks or the result will be sent back to the vehicle side. So here we mainly focus on designing a fast offloading mechanism, which is the step 3 here. So to design a scientific fast offloading mechanism, several optimization targets is considered in this work. The first is that we consider the vehicle's average data transmission energy consumption, which is quantified in this equation. Basically, it's a function of the data rate of vehicles and the channel condition between the vehicles and access point. And the second target that we want to achieve is that we are trying to minimize the vehicle's average computation energy consumption of each tasks. So basically, this cost is quantified by the vehicle's task size and the CPU frequency at the each server size and CPU architecture and so on. Okay. And the third cost that we considered is the vehicle's average task latency cost. So we want to achieve that. We hope that at the required final time, all vehicles have finished uploaded their task-related data. Well, if there is still some vehicles that cannot finish uploaded all its data, it will be punished, and such punishment is quantified in this equation here. Basically, it's just a function of the vehicle's remaining task size at the required final time here. So here's overall if a game data uploading problem. So in the cost function, we just introduce the transmission energy consumption, the computation energy consumption, and the task latency cost. And for the constraint function, the first one is the task uploading dynamics, which basically describe how the remaining task size as the vehicle set is influenced by its data rate. And also the second constraint introduced the vehicle's task size. And the third one introduced how we can control the data rate of vehicles. Okay, so here to solve the previous optimization problem, here we utilize a method called gprox PTHT algorithm. So basically, we first define a Lagrangian functional and then solve the set point problem. That's okay. So in the right table, it's just a summary of this algorithm. So I can pass it. Here are some simulation results here. So in this simulation, we use a simulator to simulate the traffic mode of traffic in the Brooklyn. And we assume that the vehicle's task size is a Gaussian distribution, and other simulation parameters are summarized in these figures. So we have some CPU frequency and CPU structure and so on. So we can pass this here. So here is a video to show the evolution of distribution of vehicles remaining task size. So this video. So also we can find out at the initial time, the distribution of vehicles task size is a Gaussian distribution as we said. And as time goes by, we can find the remaining task size gradually reduces, and finally, basically all vehicles have uploaded their task-related data. Okay, so here's a comparative experiment. So here we compare the proposed method with a very well-adapted game theoretical computation offloading algorithm utilized in edge computing. So here in a left figure, we can find that the computation time of the proposed method is very low, and the code we can also find out that the code running time of the proposed method is independent of the number of vehicles, while the computation time or say the code running time of the GTOA increases almost quadratically as the number of vehicles increases. And when the number of vehicles is 200, our method can reduce the code run time about 95% compared with the GTOA method. And also in the right figure, it's a comparison of the vehicles and the consumption cost. So here we can find out our proposed method is the cost of the that is achieved by the proposed method is a little bit higher than the GTOAs. So this is because here we utilize a mean field approximation. And so if there are the more number of vehicles there is, the more accurate the such approximation is. So this is why the cost achieved by our method is a little bit higher than the GTOA. However, we can build them in the time latency requirement. And so here is a simulation that I did utilizing the Unity 3D. So here in the right two videos, here it shows that I utilize the Unity 3D to create some traffic mode here. So here's the intersection, and here the below is the highway. So in the two figures down below, we compare the latency requirements of our method with the GTOA methods. So we can find that in the proposed solution, basically all. So here the black circle is the edge server's coverage area. The black dots are the vehicles. The green dots that are vehicles that can meet their latency requirements, but the red dots are the vehicles cannot meet their latency requirement. So in the proposed solution, we can find that basically all the vehicles have meet their latency requirements, but in the traditional solution, we can find that there are many red dots. So we can find that there are so many vehicles that cannot meet their latency requirement. So this simulation shows the great efficiency of the proposed method here. Okay, so I would like to introduce my second work that utilizes meaningful games for mobile cross-sensing. So here, first, we give a brief introduction about what is mobile cross-sensing and why mobile cross-sensing. So the mobile cross-sensing is a new paradigm that takes advantage of pervasive mobile devices to efficiently collect data, which enables numerous large-scale applications such as the agriculture monitoring, the GPS, navigation, the human body monitoring, and so on. So actually, these pervasive mobile devices includes our smartphones, our watches, the UAVs. So here, we propose to test mobile vehicles for mobile cross-sensing. This is because mobile vehicles has many advantages. For example, they can move at a very high speed so that they can be deployed very fast and flexibly. And also since they can be dispatched to different places, so they can provide large service coverage. And also currently there are many powerful onboard CPU, for example, the Tesla CPU, so they can do some data pre-processing on the onboard GPUs or CPU here. And mobile vehicles have been applied in many applications, for example, the package delivering, the Hollywood filming and sensing and so on. So here we propose to utilize mobile vehicles in the mobile cross-sensing. Well, there are many challenges that when applying mobile vehicles for MCIs. For example, the first of all is obviously since there are many vehicles, and how can we control a large number of vehicles, and also how can we save energy, and also since there are many targets, and how can these vehicles make task selection decision, and so here we propose to use meaningful game, and we focus on task selection and route planning for mobile crossings using multi-population meaningful games. This is because meaningful games can regard the large number of vehicles as a main field to reduce the computational complexity, while the traditional games or models can only deal with the vehicle separately, so that they can only have very high computational complexity. So here is a system model, or the scenario that we considered in this work. We assume that there are several operators. For example, these operators can be the Toyota, the Mercedes, the Mazda, and so on. And every operator owns a large number of vehicles. So at the beginning, this mobile cross-sensing carrier will initialize some tasks to these operators, and then these operators will dispatch their vehicles to get close to these targets, which is the red dots in this figure. And after that, the vehicles will perform the sensing tests and collect some data, and finally, the data will be sent back to the mobile cross-sensing carrier through some wireless channel. So to design such task selection and path planning mechanism, we also consider some optimization targets. The first one is that it's obviously the vehicle's average energy consumption. This is because when we are doing a path planning, of course, we want to save energy. And so such energy consumption of vehicles is quantified in this equation, where V is the velocity of vehicles and X are their locations, and omega is the sensing area, and the rho is just the distribution of vehicles here. And also, since we are planning the path, of course, we want to avoid the obstacles in the way. And every time there's a collision happens, we will punish the system, and such punishment is quantified here. So we can, which is a function basically, here the lambda is the collision economic cost, and OX is a set of obstacles position here. Okay, so the third one is the reward paid by the mobile processing carrier. Its physical meaning is just the expected number of targets that the UAVs can cover. So here it is quantified here. Here the R0 is the radius of the vehicle sensing area, and the rho X is the vehicle's final distribution, and rho Z is the target distribution. So since there are many operators that are competing against each other for the limited targets, so we assume that if two UAVs can sense a certain targets, the profit will be shared evenly. So to model such competitive behavior between these populations of vehicles, these operators will share their profits, and so this reward is reformulated into this equation here. Okay, so the last optimization target we considered is the channel capacity. So this because when vehicles are like transmit their collected data to the carrier, of course we want the data can be transmitted very fast. So we consider the channel capacity for additive West Gaussian noise channel here, basically which is basically quantified here. It's a function of the channel bandwidth, the location of the vehicles and carrier, and the transmit signal power, the channel noise, and so on. So here is overall problem formulation. It's a multi-population meaningful gain problem. Here we just show the cost function for one operator here. So for the cost function, we have vehicles energy consumption, their collision cost, their profit, and the channel capacity. And for the constraint functions, the first constraint is just the Liouville equation that describe how the vehicle's position change based on their velocities, which is the Newton's law. And the second constraint is the boundary condition that gives vehicles initial location distribution. So again, here we utilize a G-prox PDG algorithm for multi-population meaningful gain. We first define the Lagrangian functional and by introducing a dual variable phi here for all the populations. And then we are trying to solve the total point Lagrangian problem for the populations by iteratively update their strategies, their distribution, the dual variable, and the terminal distribution for these populations. And in the right table is just a summary of this PDG algorithm for this multi-population problem. So here are some videos for the simulation results. So here, this is the scenario that we built. We suppose there are two operators and there are four obstacles, which is the four blue rectangulars. And also we assume that there are four target areas. And also in the four corners, and we assume that there are more targets in the left than in the right area. And in the two videos below, it shows the evolution of distribution of these two operators' vehicles. So we can, in the left video, we can find that at the initial time, all the vehicles are located in the center, but as time goes by, these vehicles gradually moves close to the target area while avoiding the obstacles in the way. And also we can find out at the terminal time, there are more vehicles in the left area than in the right. So this is because there are more targets, and to gain as much profit, the operators will dispatch more vehicles to the left area. Okay, so and here is analysis of the competitive behavior between these operators. So there are two populations, and the populations are competing against each other. And here we plot the one-dimensional terminal distribution of these two populations of vehicles. So we can find that both of the two operators' vehicles are higher than in the left than in the right area. So this is because there are more targets in the left area, and to gain as much profit, there will be more vehicles in the left than in the right. And also we can find that operator P1 is higher than P2 in the left area and is lower than P2 in the right area. So this is because since P1 is closer to the left area, and so he can beat P2 in the left, so that the vehicles from P1 is higher than P2. Well, in the right area, it's quite the opposite. In P2 can beat P1. So okay, this is quite interesting. And next is the sensitivity analysis. So here we can, from this figure, we can find out the energy consumption, which is bar here, of the vehicles increases approximately linear with the number of vehicles. And also we can find out if the channel condition is bad, then the vehicles will consume more energy to gain as much profit. And also here we also can find out if the reward coefficient C1 from the MCS carrier is higher, which means that the operators cares more about the profit he can earn from the carrier. So in this way, the vehicles will consume more energy to gain as much profits. Okay, so here is a robot experiment, which is a real world robot experiment, show the interpretability of our proposed method. Here, the red dot is the target in the first process, and then the blue dots are the target in the second phase, and green dots are the target in the third phase. So we can find that the robots can reach the targets in each process in an energy efficient way. So this video is just a demo to show the great implementability of Minfu games in the real world robot system. So this is cool, I think. So okay, so my third work is about utilizing Minfu games for machine learning technologies. Or more specifically here, we focus on this data augmentation. What is data augmentation? Basically, data augmentation are techniques utilized in machine learning models to increase the amount of data by slightly modify the existing data or create new data from existing data. Here is two examples here. So these lines figures on the top is an image from an original data set. And by using the data augmentation method, for example, we can slightly change it by cropping it or horizontal flip or something. So we can create new images that is slightly different from the original image, but is different. Okay, so by utilizing the data augmentation, we can create more data so that the machine learning model can achieve higher accuracy. And also, since these images are different from each other, we can also reduce the overfitting of machine learning models and also promote and improve the accuracy of our machine learning model. So here is the idea of how we utilize meaningful games for data augmentation. We have two ideas. The first one is to propose a pixel level meaningful game data augment. So the idea is that suppose we have two images. We can regard the two images we can regard the image as a two-dimensional distribution. And then we can utilize meaningful game to create a path that can transform from the first image's pixel distribution to the second image's pixel distribution along an optimized path so that the points in the path can be regarded as the augmented image. Okay, so since from this idea, we can find that the start point of this image of this path is the source image P1 here. So we can here give us the first constraint here. And the question is that how can we transform from the first image's pixel distribution to the second image's pixel distribution? So we introduce a control variable u here to change the pixel value, and how it is changed, how the pixel value is changed by this control variable is shown in this constraint 2 here. Okay, so and here is the proposed Mayfield game data augmentation problem in the pixel level. Oh, so we have two images, and x is the image's pixel value, and t is the time, and u is the control variable. The row tx is just the optimized path where we want to generate, and below is the function that is the Mayfield game data augmentation problem. So for the constraint functions, it's just two constraints that I introduced in the previous page. And for the cost function, basically, the first part is that the physical minimum for the first part is that we are trying to minimizing the distance between the augmented pictures in adjacent times so that the path that we generate can be smooth and the augmented images are more meaningful from empirical evaluations. And the physical meaning of the second part of the cost function is that we are trying to minimizing the Carroll divergence between the final augmented images in the path and the target picture so that the path can gradually come close to the target image. Okay, here this is the algorithm that we use to get augmented images. So we first define a Lagrangian functional, and then we solve the saddle point Lagrangian problem by solving this optimization problem. And finally, we sampled the augmented images in such optimized path, so that we can get our augmented images. And here are some visualization results for this image level, or say the pixel level mean field game augment. So here's the results on the MNIST. So we transform 5 into 0, and 4 into 1 is 6, and 7 into 9 here. So we believe that in some intermediate time, for example, in this first video, we believe that it's looks like 5, but more like looks like both like 5 and 0, but we know it's 5. And if we fed these augmented images to a machine learning model, we believe that this model can learn the difference between the digit 5 and digit 0, so that the accuracy of this machine learning model can be improved. And down below is just some visualization results for the cipher here, like dog, the horse, the vehicle, and the bird, and so on. So later on, I will show some statistic results. Okay, so now let me introduce my second idea, that is utilize mean field game for the feature level augmentation. So it turns out that the proposed method can not just only augment images pixels, but augment their features in the latent space. So the idea is that we first compress the images into feature vectors, and then we use Mayfield game to transform from one feature distribution to another feature distribution in their latent space along a path, so that the point in the path can be regarded as the distribution of augmented feature vector. And here is the feature level augmentation problem, which is basically more like an optimal transport problem. This is because so we can still use the previous optimization problem by just replace the pixel with feature. But when we are trying to do this, here's the challenge is that so a learned feature of images is very high dimensional, about 100 to 1000 dimensional. And it will be very complex to solve such high dimensional Mayfield game problem due to the curse of dimensionality. And so here we did some revise for this Mayfield game problem. So this is a previous one. So we transform the terminal care divergence here into a hard constraint to enforce that the terminal points of the path is just the target feature set distribution. So here, this overall feature level augmentation problem here. And here we utilize a machine learning model to solve the previous feature level augmentation problem, which is a generative adversarial network. There's a generator and discriminator. The generator will generate the path between two feature distribution, and the discriminator will output the dual variable here. And the generator loss and discriminator loss is just the Lagrangian problem in the shown here. Okay, so here are some visualization results for the feature level meaningful game augment. So noticing that here what we augment is just the features. So to show some visualization results, we decode the features utilizing some pre-trained decoders here. And here is the result on the MNIST and the CFR here. Okay, so then I would like to show some statistical results. So here we compare the proposed MFG augment with some baselines like the cutout, mix, and augmix. These are very well adapted data augmentation methods in existing works. And here the baseline is just the model accuracy without any data augmentation methods. So here's the experiment on MNIST, and we can find that the proposed method can achieve the highest accuracy. And more importantly, when there's only 50 training samples, and the proposed method can also achieve 70 accuracy. So we can find that the proposed method is more suitable for those very small data sets. And next is the statistical results on the CFR10. Again, we can find that the proposed method can achieve the highest accuracy, no matter what the data size of the training set is. And again, here's the experiment on ImageNet. We can also find that the proposed method can achieve the highest accuracy. And why the proposed method can achieve the highest accuracy? So here we implement affinity and diversity metric here. So basically, these two metrics are just two empirical metrics, and here the affinity can quantify how much an augmentation shifts the training data distribution from that learned by a model. Well, and the diversity quantifies the complexity of the augment data with respect to the model and the learning procedure. So typically speaking, if a data augmentation method with the have a higher affinity and diversity score, they really can achieve better performance compared with those with low affinity and diversity score. So in this figure, we compare the proposed method with cutout, mix, and omics, and we did 5 independent experiments, and we plot the whole results here. So we can find that the meaningful game augment can achieve the highest affinity score and diversity score compared with this baseline, so which can prove that can illustrate why the proposed methods can have the highest accuracy when tested on some image dataset. Okay, so finally, I want to later I will introduce my fourth work that utilize meaningful games for the satellite-based federated learning. So first, what is federated learning? So it is a decentralized approach to machine learning where devices train their models locally and share only the model updates with a central server. And we believe such paradigm can enhance the data privacy and reduce data transmission between the clients and the servers. And compared with traditional centralized machine learning frame, federated learning has many advantages. For example, they can preserve data privacy and promote security, and they can help to reduce the data centralization, and it can be extended to a very large client networks, and so different clients can have its own models. So this for the model personalization, and also it can help to improve bandwidth efficiency. And in the right figure is example of the federated learning applications called the text prediction. Actually, this is introduced by the Google. Okay, so here well, there are some challenges in the traditional terrestrial communication-based federated learning. So they utilize terrestrial communications. And here we propose a satellite communication networks instead of the terrestrial networks. Just because compared with the terrestrial networks, the satellite communication networks has many advantages. First of all, it can provide a global coverage. Since the satellites are moving at a very high speed around our Earth, and so they can be deployed very quickly and flexibly, and also it can provide very cost efficiency services for those wide areas and can achieve high broadband capability. And actually, right now there are thousands of satellites flying around our Earth, and there are many companies work on satellite communication networks. For example, the Starlink, OneWeb, and Project Cubitor, and so on. So here we propose a satellite communication-based federated learning network, where the devices serves as local clients, and satellite serves as servers in the federated learning. And some applications are very appropriate for these traffic processing, for example, and the location-based recommendation and pollution monitoring, and so on. And in the right figure is the workflow of the scenario that we consider. In the first step, the devices on the ground will update their model parameters, and after that, the model parameters or set of model updates will be uploaded to the satellites, and then the satellites will aggregate the model parameters, and finally, the model parameters or the model update will be downloaded to the devices on the ground. Well, there are many. So here we focus on designing an incentive mechanism, and there are many challenges. The first one is that since there are large number of devices on the ground, and how can we deal with the scalability issue? And also, many of these devices has very limited battery, and how can we deal with such issue? And also, since the satellites are moving at very high speed around the Earth, and at the same time, one vehicles can see many satellites in the sky and can communicate with them. How can the local devices make their server selection strategy? And also, since satellites are moving very fast, and when satellites moves out of devices reachable area, how can we design our handover mechanism? So here, we propose a joint server selection and handover design optimization problem. And we assume that there are M devices and N satellites, and we assume that the M device owns the M data quantity, and the M device decides the probability strategy to select the N satellite, and the satellite decides the handover action. And to design such server selection and handover mechanism, we consider several optimization targets. The first one is that we want to minimize the device's combination cost as much as we could. So such cost is quantified in this equation down below here, which is a function of the model size in the federated learning, and the channel condition, and the device's action profile. And we also consider the payoff from the satellite N for device M. So this is because if there's no payoff, no one will want to join this federated learning process. And such payoff is quantified in this equation. The physical meaning of this is basically quantified by the profit that the satellite can achieve. So basically, it's a function shown here. Here we have the data quantity that model owner K has, and the profit. And so here it's worthwhile to mention that f is an empirical function. So basically, from some empirical stylings, we find that the model accuracy of a global model in federated learning can be approximated by a log-like functions with the number of samples that is used in this federated learning process. So here we just utilize empirical log-like function for this f. And also, since these devices shared the profits, and how the profit is shared is basically quantified by the device's data quantity and their contributions. And finally, we add a composite term to this payoff. And the third cost, or the third optimization target that we considered, is the handover cost of device M to choosing satellite N, which is shown in this equation here, which is a function of the constant transmission power of the satellite to satellite communication, and also is a function of the remaining task size of the handover data and the capacity of the intersatellite link between two satellites. So here it's worthwhile to introduce the sigma here. So here the sigma is an indicator variable that indicates whether this satellite needs to hand over its data for the device M. So it's highly predicted. This is because the satellites, when satellites are flying in our sky, orbiting, their trajectory are highly predicted. So this is why this sigma is usually a given indicator variable. So to summarize, here is our all joint server selection and handover design optimization problem. So for the cost function, we have the payoff of devices, their completion cost and satellite handover cost. And for the constraint function, since the devices strategies is probability strategy, and so it should be a positive number, and also they should be sum up to 1. And in the third constraint is just gives the available satellite set as the kth communication round. So we are trying to minimize the cost of the devices and satellites in all communication rounds here. Okay, so to solve the previous algorithm or previous optimization problem, we utilize an algorithm named mean-field evolutionary approach. So basically, there are 2 steps for this approach. In the first step, we construct a strategic graph for the clients. So the nodes in such strategic graph is just the strategies of agents, while an edge exists between 2 nodes if the agent strategy can switch from one strategy directly to another strategy. So here we utilize a fully connected strategy graph. This is because there is no limitations for the agent strategies. So after construct the strategic graph, in the second step, we define our focal point dynamics as the gradient flow based on such strategic graph. And here we have the agent strategy, which is P here, and here F is cost function. So we iteratively update the agent strategy along this focal Planck dynamics gradient flow until convergence, and then we can get the optimal solution for these optimization problems. Okay, so here are some simulation results. So in the right table, it's just some simulation parameters, so such as the device's data size, their contribution index, their power, and also the satellite's power, the channel condition, and so on. And below is there are 4 figures that shows the algorithm convergence behavior. So in the first figure, we can find that this figure plots strategy for a reference device here. So we can find that after about 60 iterations, the algorithm converges, and also it's quite similar as the convergence behavior of the 3 figures left. such as the communication cost, the payoff, and the handover cost. Okay, so next I would like to introduce performance analysis. Here we compare the proposed method with the random strategy. So we can find that the combination cost can reduces about 10.5%, and the payoff increase about 6%, and handover cost reduce about 82%. And also did sensitivity analysis. Here we did a sensitivity analysis of the communication cost and overall cost with respect to the channel gain. So we can find that the channel gain is really an important factor on the cost, and also the communication cost and the overall cost increases as the channel gain reduces here. And here is a comparative experiment. So here I compare the proposed method with a very well adopted method called the replicator dynamics. So here we compare the performance of this method in terms of the code running time and the optimized cost. So in the left figure, we can find that the code running time achieved by the proposed method is much lower than the replicator dynamics. And it can reduce the code running time about 80% compared with the replicator dynamics algorithm. Also in the right figure, it shows the optimized cost achieved by these three methods. Again, we can find that a proposed method can reduce the cost about 31 compared with the replicator dynamics and 33 with the random strategy algorithm. Okay, so here is the conclusion of my today's presentation. So in this presentation, I introduced Minfield games. So Minfield games studies the strategic behavior of a large number of small interacting agents. And by applicating the population behavior, Minfield game can reduce the computational complexity significantly. So later on, I introduce my 4 works that utilize Minfield games for the applications in machine learning and 60 communication networks. The first work, I introduced Minfield game to design a fast offloading mechanism for vehicular edge computing. So we can find that the Minfield game can reduce the code running time significantly, and we also show a real-world implementation in the Brooklyn traffic mode that shows the great efficiency of the proposed offloading mechanism. And then in the work 2, we utilize Minfield game, which is a multi-population Minfield game for the task selection and path planning in mobile cross sensing. And here, Minfield games can reduce the system complexity and also implement the Minfield game in a real-world robot experiment that shows the great effectiveness and implementability of the Minfield game. And also in the work 3, we utilize Minfield game to design a data augmentation method in machine learning. And we can find that Minfield game can summarize. So here, an image or the features are regarded as a large population system. And we can find that Minfield game can summarize the whole pixel or feature information of images. And from the experiment, Minfield game augment achieves highest test accuracy. And in the work 4, we utilize Minfield game for server selection and handover design in sitcom-based federated learning. And we utilize a Fokker-Planck equation to update the agent strategies. And we can find that it's quite efficient to update the strategy. And we compare the proposed Minfield evolutionary method with some baselines, and we can find that the Minfield game can reduce both the code running time and the optimized cost compared with those state-of-the-art methods. So here's my future works. So in my future work, I may connect Minfield games with graph embedding reinforcement learning route design. So I may connect Minfield game with the reinforcement learning with federated learning in satellite connection networks, and I may use Minfield game to simplify the devices and satellite strategies. And I may also combine Minfield games for reinforcement learning, in that I may utilize a reinforcement learning model to learn the Minfield game equilibrium. So actually, there are already some works working on these topics, but here I may propose a different Minfield game version Markov decision process, and I may focus on some engineering applications here. Okay, so and here are some publications during my PhD study. So a book and some conference papers and some journal papers. Okay, so thank you everyone. Thank you so much for your time listening me for this dissertation presentation. So if you have any questions, please ask. Thank you.
Okay, thank you very much. Let me stop recording first.